Hey everybody. All right, so let's talk about our unit lab. So we're going to be doing a virtual lab on an inclined plane. So an inclined plane is just a ramp, basically. Okay, so we're going to have to figure out what the physics looks like on a ramp. So we're not going to be able to do this like in a lab situation where we use ticker tape timer and a dynamics lab and all this, dynamics cart, sorry, and all that sort of thing. We're going to be using instead a virtual platform. On the lab sheet, the first thing it tells us to do is to go to this website. And you'll see it looks like, where are we? Like this. Okay, so this is our website. And this is the original settings. We're going to change these slightly. So we're gonna start off with no initial velocity, so the free fall case. So move that slider until it says 0, and we're going to get rid of all the friction. So we're going to have an idealized frictionless situation. Okay, and then you have a little bit of choice here. You can change somewhere. Pick a angle somewhere between 25 and 35 degrees. Okay, so let's go 27.9. Write that down somewhere. And then our mass, it asks us to set the mass slider to a value between 5 and 10. So 7.5 sounds good. Okay. So we're going to run this experiment now because we can actually, you could just run the experiment and it'll look like this. But instead we're going to do a bit more carefully. We're going to use these step buttons. So right now the time is 0. And I'm going to step through the times, these hundredths of seconds, until I get to 0.1 second. And now the time is now 0.1 second, and the displacement is now 0.02 meters. All right. So when I go to my, apologies, to here, I can have, it says ticker tape time. This is the lab I would use from an actual ticker tape timer lab, but we're just going to reuse the sheet here. So these are my time intervals. So between my time interval of 0.0 seconds to 0.1 seconds, my displacement is 0.02 meters. So that's going to be 2 centimeters. Right? So you're going to put 2 centimeters down here. Then the next one, we're going to keep going. And now it's going to be 0.09. Now we're going to have to be careful here. This 0.09, this is the total displacement from the beginning in the first 0.2 of a second. Okay, so that's the total. In my chart, it's asking for the displacement for this time interval. So we're going to subtract the previous number. So we're now going to, instead of saying 0.09, we're going to say 0.07 or 7 seconds. So let's write these down. Okay, so this was going to be 2, and this would have been 9 take away 2, which is 7. Okay, notice I'm not putting units on here because whenever you do a table and you put the units at the top, you don't have to put units as you go down. All right, so let's do this again. I'll do one more. We're going to get to a time of 0.3 seconds, and now we've gone 21 centimeters. So that's going to be my total here was that would be 29 take away 9, right? Because altogether in my first 0.2 seconds I went 9, so that's going to be an additional amount of 21 take away 9, which is 12. All right, so now I've gone 12 centimeters in that next chunk. All right, and we can keep going. So now I have 0.37. So that's going to be 37. So this is going to be 37 take away 21, which is, what's that? It's going to be 16. All right, and we can just keep going on with that. All right, so once we're going to come up with a full table here for all of my data, all of my displacement data, and then somehow I'm going to have to jump over from displacement data to velocity data. Now, how am I going to do that? Now notice this is the displacement for this time interval, and these are instantaneous velocities at a midpoint of the interval. In the middle of 0 and 0.1 is 0.05. Now, this is going to be a little bit beyond this class, but that's okay. We're just going to prove why this is the case. So, if I have a time interval, say between t1 and t2, and I have some curve here, if that curve is quadratic, right, x squared, right, remember quadratic means y equals x squared. If I calculate the average rate of change, average rate of change involves creating a triangle connecting the dots. Right, so this would be the displacement. I'd get a triangle here, some delta d, and I'd have a delta t, and I would calculate the slope of this to get an average rate of change. Okay. Now, what's interesting about quadratics is that average rate of change over the whole interval is equivalent to the instantaneous rate of change at the midpoint. Those two slopes, the rate of change, the slope of those two blue lines are the same. And to prove it, we would require a bit of calculus. It's not that difficult once you have some differential calculus under your belt, but it's true. Just believe me, okay? So average velocity over the interval t1 and t2 is equal to the instantaneous velocity at the midpoint, right? The average of the two times. And this only works for quadratics, and we know that this is going to be quadratic because we have no initial velocity and that my acceleration is a constant. It's g. All right, so that's why, let's go back here, I can just calculate here my instantaneous velocities. This is going to be very easy because all of these delta t's on each one is always 0.1 seconds. So for me, my goodness, sorry, writing on a tablet is difficult. So the time is always delta d, 0.1 seconds. My displacements are always here. Right, these are my delta d's in this column. So then to get my instantaneous velocity, I just have to divide delta d by delta t. So 2 centimeters is going to become, if it's always divided by 0.1, that's the same as multiplying by 10. So this will be 20 centimeters per second. Next one will just be 70 centimeters per second. 120 centimeters per second. Okay? So we can come up with these instantaneous rates of change quite easily by setting it up this way. All right? So there's that. Okay. Then I'm going to ask you to come up with a VT graph. So you're going to take your instantaneous velocities and make a VT graph. So you're going to basically, let's go back here. Sorry, keep going back and forth. So you're going to graph, this will be on our x-axis and this will be on our y-axis. We're going to make a VT graph. So putting all of our times, our midpoint times, and all of our instantaneous velocities, we're going to make a graph out of that using Excel. And if you have any problems with Excel, there is a video on the home page on how to use Excel. I made it last semester for the pendulum lab, but that's okay. The exact same tricks are all in there. How to take your data, how to make a scatter plot out of it, how to then create a line of best fit and get the equation for it. Okay, so that's basically what we're going to do. We're going to create a graph using Excel. Then we're going to put a line of best fit onto our data, and then we're going to use Excel to give us the equation for that line of best fit. And once we have an equation, once we have a value for acceleration, we can use the formula in question 3 here, this equation here, to calculate g, the acceleration due to gravity. It's going to be our value that we calculate in our lab divided by the sine of the angle of our system. Okay, I can't prove that. That's basically the first lesson in grade 12 physics is proving that equation. But at this point, don't worry about it. Just plug it in, plug in your number, divide by sine theta, whatever the theta was from your system, and we're good to go. All right, and then there'll be a couple questions. So discussion questions. If we had done this lab in the classroom, would the value that we get be lower or higher? So would you expect that you get a higher or lower value, and why? Basically, what does friction do to our system? Because that's what we're missing in this problem, is there's no friction. So what would friction do to our system? And then number 2, what would happen in our graph? How would the graph change? What would the shape of the graph change if we'd done the exact same situation, exact same lab on the moon, or if we did it on a super Earth that's triple the mass of Earth? How would that affect the shape of our graph? Okay. All right. What about expectations for the lab? So I've attached. Where is it? Lab expectations. This is what I would give my class in North Grenville. This is the just typical science lab report criteria. Okay. So first thing we have to have is a title page. Okay. So make sure you have a title page. Choose an appropriate title. In the bottom right-hand corner, make sure you have all your information: your name, date, course code, my name. Now that's all you need, because we don't have a room, or there won't be any group work in this. Okay, so make sure you have it. That'll be our first thing, a title page. Then you're going to do an introduction. Now, it is listed here as a bunch of things, but really, I don't want this. I want a page double spaced. Can I write on this? No. I want a page double spaced of basically what, let's say, a grade 10 student who's never done this before would need to know about acceleration and gravity and displacement and velocity to do the lab. To understand the background knowledge. So really, I'm just looking for a sort of background information review of all the things that are required, the sort of background knowledge you need to be able to do the lab. Okay, and buried in that text, in that paragraph, you should have important terms defined, and basically, what are we trying to do? What's the point of our lab? Okay, please don't write, A, background information, and then a bunch of stuff. B, important terms. C, don't do that. I just, these 3 things have to be in it, but lay it out as a page-long paragraph. Or you can do multiple paragraphs if you like, but just double spaced, typical, Calibri 11 font, 1 page. About all the background information and why are we doing this lab? How are we doing this lab? This is probably going to be the newest, most challenging part of labs for you. You may have done this already, maybe, but probably not. Okay, so it's very important though that you basically set the stage for all the things that we're going to do in the lab. Then you're going to have a hypothesis. In this, we're not going to have a hypothesis in this lab. Okay. Typically, you would have some sort of, I think that, but in this case, we're just going to skip the hypothesis. Then design, materials, and procedure. Basically, go over the procedures that I laid out for you guys, but write it as a formal procedure in paragraph form. Do not copy the steps involved, and you have to talk in the past passive voice. Okay, no I's, we's, and that sort of stuff. Okay, we're going to talk about it's an impersonal format in the past tense. The water was added. Okay. And always state the source. So at the end, say, for more information, see lab sheet. And then you can make sure you have a picture. The picture is going to be basically, just take a screenshot of this. That can be your picture. Hopefully you guys know how to get screenshots. You can use the snipping tool. If you're using Windows 10, just go to the search, type in snipping tool, and it should come up, and you can easily take just you don't have to take the full print screenshot, but just cut out what you need from this. Okay. Observations, that'll be tables. So back up a little bit here. Yeah. So the observation, that's going to be a table. And it's going to be called table 1 and table 2, just like in our lab sheet. Okay, this is going to be the actual data. Right? So make sure you label it table 1, displacement of our cart. Table 2, velocities, instantaneous velocities of the cart. They are labeled already on your thing. You should be able to just copy them down. So in Word, make your own little tables and put the data in there. Okay. Then we're going to make a graph. I would actually prefer the graph in the analysis. I know it says here graphing data here, but I would like this graphing part under the analysis. That's the how we analyze the stuff. Okay, so let's go back here quickly to my actual, where's the sheet? There it is. Okay, if you go back to the actual sheet, you can see here it says analysis. So just for analysis, just go number 1, make your table in Excel, copy and paste it into Word, and we're good to go. 2, get the line. So the number 2 will be answered with your graph from Excel. So just write down in a sentence, the slope of the line is such and such centimeters per second. Now be careful. 3 asks for it in meters per second squared. So you're going to have to do a little conversion between centimeters per second squared and meters per second squared. Okay. And then we're not going to do sources of error in this one because we don't have any errors in this. But that's basically just going to be your discussion. And we're not going to put any applications. And then just make sure, very important, that you have a reference place. So when you're doing your research for your introduction, any websites you use, make sure you use APA format, okay? And then at the bottom of the sheet, just a quick little table for all lab 1, 2, 3, 4, 5 for the course, and just to help you guys check off all the things we need. So just for lab 1, we will not be having a hypothesis, okay? And we will not be having applications. So don't worry about hypothesis and don't worry about applications. Everything else should be there. So title page, right? That's a 1-page appropriate title and your name and all that sort of information on the bottom right. Introduction, that should be a page about all the things you need to know and why we're doing it. Design material procedures, so there's a paragraph explaining what you're doing, passive voice, and a picture, screenshot in this case. Observation is going to be the tables. Analysis will be questions 1 through 3 in the analysis section, and then there's going to be an evaluation, the discussion as well in that. And it doesn't actually say here, but did I forget? Oh, conclusion. Make sure that you have a conclusion. Just a final little sentence or two, what was we had a purpose, right? In this case, it was determining what the acceleration due to gravity was. So the acceleration due to gravity calculated from our lab is such and such. Done. Okay, and then references. All right. So those are all the things that you need to do for a formal lab. When we do labs in this course, they're all going to be formal labs like this. Oops. Where's my hand? There it is. No. Okay. Anyways. All right. So if you have any questions, feel free to ask me on Teams or send me an email about how to finish labs. But I think that's all I want to say about labs for now. All right. So I'll be talking to you later. Best of luck.